This video will give another example of graphing a polynomial to go along with those that we covered in class. In this example, I'll work with a non-factored polynomial. If it's non-factored, that means that the polynomial is in standard form. Here's an example. Looking at this function, we can see, since it's in standard form, that it is a quartic because the highest degree is 4. It's also a trinomial because it has 3 terms. Another thing we can see from this form is that the constant, the term that would usually just be a number by itself, is 0, which means the y-intercept in this case is 0. To get the x-intercepts, we always let y equal 0, and when this equals 0, there's not much I can do with it in this form, so I'm going to factor it so I can set each of the factors equal to 0 and find my x-intercepts or my zeros. To factor this, I would start by taking out the greatest common factor, which in this case is 2, because all of the terms are divisible by 2, and x squared. And what I'm left with in the first term is x squared, minus 2x for the second term, minus 8. So we've already started factoring this. I can see one of my factors already. So 2x squared is one of my factors. If I set it equal to 0, I would get x equals 0. However, this trinomial over here, since it's a quadratic, can be factored further. So if we factor that further, maybe you've already done that, it can factor into x minus 4 times x plus 2, the quantity, okay? And so if I just bring the first term down, or the first factor down, we have this for our fully factored form. And now I'll set each of these equal to 0, and so that gives me x-intercepts at x equals 0, x equals 4, and x equals negative 2. So we have 3 x-intercepts. The x-intercept, or 0, at 0 is going to be special because that factor has an exponent of 2. And as we saw in the recent investigation we did with the TI-Nspire calculators, if one of our factors, or if a factor I should say, has an even exponent, then the graph will just touch the x-axis at that 0. It will not cross through. It's called a bounce point. So you can think of it as bouncing back off of the x-axis. In order to now sketch this graph, I need to put together some of the different things that I've mentioned. I did talk about how the y-intercept was at y equals 0. And we also talked about how the degree was 4, coming again from here. So with that information, the degree being 4, and the lead coefficient being positive, I know my end behavior is going to act the same as a quadratic, which also has an even degree. So it's the same thing when the exponent is even and the coefficient is positive, then the graph's end behavior is going to be up, up. If this were negative, but it's still even, it would be down, down. So this one's going to be, for end behavior, up and up. As I've mentioned, I know that there's going to be a bounce point at x equals 0, and it will cross through the x-axis at x equals 4, and again at x equals negative 2. So let's put this all together on a graph. I've plotted the x-intercepts, and one of them happens to also be the y-intercepts, so we're going through the origin there, or bouncing at the origin, I should say. So now that we have our x-intercepts graphed, I like to look next at the end behavior. So this is what's happening at the far left of the graph and the far right of the graph. And we have here the only 3 places on the entire graph from negative infinity to infinity. These are the only 3 places where the graph will touch or cross the x-axis. So if I look at, as I come in from negative infinity, if I look at the first 0 I come to, negative 2, then before this, the end behavior must be going up. It can't go back down because it would cross through the x-axis again, and we would have gotten another x-intercept when we factored. So this is the first time it crosses the x-axis. And so we know that coming from this point, the graph must be going up and to the left. Or as I come from the left, it's going down and it's going to cross through at -2 because we said there's a cross at x equals -2. So let me draw that part in. So I'll just start with this part. We know it's going to go up from here. And then I know it's going to go down. Don't worry too much about how far it's going to go down. You'll notice I purposely did not label the y-axis, even though I'm always telling you to put your scales. In this case, we don't really want to scale. We're just going for a rough sketch. So I've gone down, I crossed through, but then the next piece of information that I have is that there's another x-intercept at 0. So this graph, while it's going down, is going to have to turn back around to get up to this point. And at this point, we know from our information up above that this point here, this x-intercept, is a bounce point. So the graph is not going to go through here, it's going to bounce back off. So I turn around, don't worry about exactly where, and I'm going to go up, touch that x-intercept, and bounce back, in this case, down. So now I'm going to go down for a bit. I'm going to go down further here than I did over here because there are only 2 units to play with in between my 2 x-intercepts here, but over here there are 4. So I can go down further because I have more time or more room to turn back around because, as we know, I have to also cross through this point, and after that I'll put my end behavior that's going up. I could have, when I put this end behavior in, gone over here and put this one in right away because I know this is the last place that it will touch the x-axis, so I could have done that first and then gone back and said, okay, well fine, this was going to go down and then it's going to turn back around and go back up. So the graph would look something like this. Is this a great sketch? Maybe not. I would imagine that it's going further down here. But as long as you go down further here than you did over here, you're in great shape. So this is a rough sketch of this quartic function that I gave you. On the next slide, I want to review how we would convert from factored form into standard form. In this example, I went from standard form into factored form. Make sure you get the heading into your notes for converting polynomials from factored to standard form. And let's look at an example. Here we have a cubic that is in factored form. I know it's a cubic because over here, if I expand, I will get an x squared term. And eventually I will multiply that x squared term by another x, giving me an x cubed. So this is a cubic, which will be easier to see once we expand it out. There are a few ways you could do this. If this 2 weren't here, so if I just mark it up for a second, if this weren't here, then we all know how we would do this. I would expand by doing the first terms multiplied together, and then the outer terms, and then the inner terms, and then the last terms. And we would get a quadratic. But in this example, we know we're going to get a cubic. So I could either start by expanding this out further and saying this is equal to x plus 3 times x minus 2 times x minus 2, okay? And then I can choose whichever 2 binomials I want to multiply first. My personal preference is to multiply the last binomials together first because then I'm distributing this from the front. It is going to give the same answer if you choose to do the first 2 multiplied together first and then distribute this into that. So whatever you choose. So if I expand out the 2 binomials at the end, I would get x squared, and when I do the outer and the inner term, I get minus 2x for both, combined as minus 4x, and then plus 4. So that's the last 2. I still need to distribute in the x plus 3. So I have to do this term, distribute it into all 3, and I'm multiplying. So that would give me x times x squared is x cubed. X times negative 4x is negative 4x squared. And x times 4 is 4x. And now I have to distribute the 3 to all three of the terms. And so 3 times x squared is 3x squared. 3 times negative 4x is negative 12x. And 3 times 4 is 12. So here it is all expanded out. I'll put back the y equals here. And now I'm going to go through and combine like terms. I have two x squared terms. So there's my cubic term. You can now see the degree is 3. When I combine my x squared terms, I get negative 1, or just negative x squared. I'm going to combine my two x terms. 4x minus 12x is negative 8x. And then the last term, the constant term, is 12. From this, we can see that our y-intercept is 12. Again, as we said, it is a cubic function. The degree is 3. It has 4 terms. We don't have a special name for that. It's just a cubic function with 4 terms. And the other thing I can see from this form is the end behavior. Since we know it's the cubic and the lead coefficient is positive, the end behavior for this would be down, up. But other than that, I can't get much more from standard form. It's easier to graph it when it's in factored form because I can see my x-intercepts and so on and so forth. So we'll practice this more in class. I hope you enjoyed this video.